This is a step-by-step tutorial on using nonlinear confidence intervals. I'm going to run through an example which is an Arrhenius expression using A and EA as my parameters. Those are the ones that I can adjust to fit a model. So first of all, I have measured temperature and then a measured rate constant K. So measured temperature T, number of temperatures, and then a number of rate constants. I may have extracted that from a single reaction experiment. Okay, and then I also have model predictions. Those come from the Arrhenius expression that you can see up in the upper left hand corner. So I took the temperature with my values of A and EA, those were my guess values, and then I predicted a K. And then I computed an error for each one. Now the error in this case is just the measured minus the predicted squared. So I have a squared error, and then I'm going to sum those up. I'm going to have the sum of the squared errors, they're SSE, and so I have the summation of my error. Okay, now I can minimize this to obtain my A or EA. Another way is to fit, this is just a simple Arrhenius expression. I have all of my points plotted. I can fit a line to that, and for this simple case, this works. For more complicated systems, this may not work. I'll just show this for the line. I have my slope M, and then my intercept B for this line. And then I'm going to go ahead and write my Arrhenius expression. My K equals A times the exponential of negative EA over RT. E or EA is the that is the activation energy, and the A is the pre-exponential factor. So I'm just going to take the log of both sides, and I'm going to linearize this. Okay, so ln K, the natural log of my rate constant, that becomes Y. Okay, and then the natural log of A, that becomes my intercept, and then negative E over R, that becomes my slope, with 1 over T becoming the x-axis value. Okay, so my slope is negative E over R, and then my intercept is natural log A. Okay, so then I can compute the value of A and EA just from this linear regression, and you can see they're fairly close to the optimal, to my my actual parameters, and my ones that I calculated are fairly close. Another way to do this is through a sum of squared errors, an optimization approach, where I try to minimize the sum of squared errors by adjusting the parameter values. Okay, this is a more general approach that works well for almost any modeling system that you want to address. Again, I'm just showing it for the simple equation. There's my optimal solution when I use the Excel solver to calculate the minimum sum of squared errors. My pre-exponential factor A was 9027, and there's my sum of squared errors. That's my best objective value. Okay, and so that's my sum of squared errors at my best, the best combination of my parameters. Often we're going to call these, well, for this derivation we'll call them theta, all of my parameters. So A would be theta 1 and EA would be theta 2. Okay, and then I'm gonna go ahead and scroll down. I'm gonna now define my theta star as my best parameters, and then S of theta star, that's the sum of squared errors at my best parameters. Okay, so S of theta star is the 142,000, and then theta star 1 was 9026. So I'm not going to do an F statistic. I'm going to use a Ftest. You don't want to confuse those two. Ftest is a statistical test. Essentially, one of the purposes of it is to compare how well two experiments agree with each other, or if you have confidence that two experiments or two tests are aligned. And what we're going to do is we have two tests in this case. The first test The first test is, or experiment, I guess if you could call it, was fitting our parameters to the available data. And what I'm going to do is perturb those parameters away from the optimal value. So the S theta without the star, those are the non-optimal values. And then minus S of theta star, those are my optimal parameters. Okay, so the difference between those is in the numerator. And then the denominator is just the sum of squared errors at the optimal values. This has to be less than or equal to P over N minus P. And then I have my Ftest there that can be computed with a number of software packages like Excel or MATLAB or Python. Okay, so in the numerator I have P, which are my number of parameters and number of measurements. And then I also have my my Ftest parameters there. There's 3 that you give to be able to calculate the F value. One is alpha, that is my 1 minus alpha is my confidence level. So if I have a 95% confidence interval that I want to compute, then alpha is going to be 1 minus the confidence level, so 0.95, and that is going to equal 0.05. Okay, so alpha equals 0.05 for this case. Again, we're comparing the optimal solution to a suboptimal, and we're determining if there's a 95% confidence that the non-optimal is equal to the optimal. Okay, so what I'm going to do is then take these parameters and I'm going to adjust them away from the optimal solution or the optimal value. So that's going to be my second test. Is going to be adjusting those away from the optimal values. And there you can see I have my A values that I've adjusted down, so those are the negative, and then also above. And my sum of squared errors is going to be worse for either moving it up or down, so away from my solution. There's my optimal value, my best objective, and then as I move my A value away from that, my sum of squared errors is going to increase. That's the blue line. Okay, and then I compute with my Ftest, my fractional cutoff, and then also my objective cutoff. So wherever my sum of squared errors is less than that value, that is my 95% confidence interval. So in this case, A is less than 90-40 and also greater than 90-15. Okay, so that's my confidence interval for this system. Okay, now I'm going to move over to doing this in MATLAB and Python. I'm going to visit the APMonitor.com website, go to the optimization course, and here in the optimization course I'm going to go down to a kinetic modeling. Go down to the kinetic modeling assignment and you'll see a number of files that you can download for this. Okay, so here's the nonlinear confidence intervals in MATLAB and Python. Go ahead and download that and then open it up. It's just a zipped archive. Go ahead and extract those to a folder that you have. This should work on Mac, Windows, Linux. It should be able to work on all platforms. Okay, now I'm going to first of all just go ahead and open up the Python file. I'm going to open that with the IDLE, the editor. It shows the syntax highlighting. Then I'm going to go ahead and run this with either hitting F5 or by the menu option there. And there you can see my confidence interval for, in this case, this is for the dye fading experiment. This actually included some real data, and there you can see the confidence interval for A2 as well. So there are actually 6 parameters in this case, and you can see the different confidence intervals. These are nonlinear confidence intervals for each of these parameters. Okay, now I'm going to close this out and then open it up in MATLAB just to show you that this can also be computed with MATLAB. Go ahead and run it, and then you'll bring up the same confidence intervals. So we reviewed 1D confidence intervals, nonlinear, Ftest. Let's talk about how to obtain these confidence intervals for parameters that may be correlated. So if I change the value of one parameter, the optimal value may be different for the other one. So I have my A and then my EA. Those are my theta, my parameters. I'm going to plot the optimal value of A versus EA. So let's say I adjust the value of A independently and then recompute an optimal value of EA at those points. So this A might be fixed by me, and then EA would be calculated by an optimizer. Okay, so this might be how the two parameters are correlated. And then for our test that I just, the video and example that I just showed, we had an A value, an optimal value, and then we moved that value away from the optimal solution. Okay, so then I'm going to put my confidence interval here on this plot that we just computed. Okay, so you had a range. That's a 1D confidence interval. But for the case where the parameters may be correlated, as in the Arrhenius expression, I'm going to go ahead and plot the optimal values, and then also plot my Ftest results. That's for A, and then I could also do the same for EA at those values and compute a 1D confidence interval. And I'm going to combine those into a 2D confidence interval. So this looks kind of like a banana, okay, a banana-shaped function for the 2D nonlinear confidence interval. This two-dimensional region is then the region where my sum of squared errors is less than that same Ftest that I had performed previously.